So here we go, ladies. So now that you have practiced drawing your isomers and being specific with the name, we're going to put it into play. All right. And we're doing it in this way where you're going to be looking at mainly the reactions of these things. So we're going to look at these organic compounds individually. We're going to look at alkanes, we're going to look at alkenes, then alcohols, and then acids. All right, before we go any deeper in organic chemistry. Now, there are a few things that we will look at for all of them. One, we look at the characteristics of them. So for each of them, we will look at the characteristics. We will look at how they are made, meaning that the manufacturing of these substances. We will look at the reactions of these substances, right? And any test that is associated with it. All right, as well as the uses of them. That's the one I was trying to remember because I know it's 5 of them. And the uses of these substances. All right, so let's go. All right, so hydrocarbons are made up of carbon and hydrogen atoms. It says that hydrocarbons, the structure consists of covalently bonded molecules. And of course, that's how we have been drawing them. So when we draw the fully displayed structure and we draw the sticks in between, that stick in between represents a pair of electrons that have been covalently, right, bonded between the carbon atom and the hydrogen atoms. Now, the thing about these covalent bonds is that they are weak. So they are known as weak van der Waals forces. However, the forces will increase the larger the molecule becomes. So what are they saying? The more carbon atoms that you add in your chain is the stronger these covalent bonds become, right? So what is expected? Since the more carbons we add is the stronger these particles get, there is a steady variation when it comes on to these hydrocarbons. So this is what they're saying. The boiling point, right? Viscosity, and viscosity should so familiar because you guys do physics. Boiling point and viscosity. Viscosity, look at how thick it is. Density, how heavy it is, will all increase with increasing number of carbon atoms. So an organic substance, a hydrocarbon that has 5 carbon atoms in the chain would be or would have a lower boiling point than a hydrocarbon with, say, for example, 20 carbon atoms in the chain. It will also be less dense. The one with the 5 will be less dense than the one with the 20. Right? Now, there's also a steady variation when it comes on to the state of matter. And this is something that you must make a note of. All right, ladies? So, if in my carbon chain, I have 1 to 4 carbon atoms, then the state I am in at room temperature is a gas. 1 to 4 carbon atoms are gases. So if I have, for example, methane, propane, butane, ethane, these are all gases at room temperature. So think about it. I always tell you that your cooking gas, the one in the cylinder, is propane. And of course, you can make the connection now. Propane, cooking gas. All right. So once you have carbons 1 to 4 in the main chain, then it's a gas. 5 to 15 are liquids. And then lastly, 16 and over are solids. All right. Now, how do alkanes behave? The thing about alkanes, ladies, remember when we looked at the term saturated and unsaturated compounds, we read that alkanes are saturated compounds. Now, it is almost as if you're looking at the atomic structure. And when we look at the atomic structure and we say that, okay, the outer shell is full, the valence shell is full. And so when the valence shell is full, these substances are unreactive. It's pretty much the same with the alkanes. Alkanes have maximum number of bonds surrounding their carbon atoms, and these bonds are with hydrogen. So they have the maximum number of hydrogen atoms around it. So you know what happens to alkanes? Alkanes are pretty unreactive, right? So alkanes are relatively unreactive molecules. They are pretty much stable because they have maximum number of hydrogen atoms surrounding their carbon atoms. So there are only two reactions that we're going to look at for alkanes. The first reaction that we're going to look at, ladies, is combustion. That's the first one. Now, combustion is a reaction that we learned about when we started looking at types of reactions. So you learned about synthesis and double displacement and all of that good stuff. Now we're learning about combustion. Combustion of hydrocarbons, aka my alkanes, is a reaction that takes place in air. So it's burning in air or a reaction with oxygen. It produces only two products, carbon dioxide and water. So guess what? It doesn't matter the alkane that we start off with. I could have used methane, propane, hexane, whatever else ane there is. When these alkanes undergo combustion or burning into the air, only carbon dioxide and water are produced. What makes a difference in the reaction, ladies, is when we have to balance off the reaction. So how many molecules of this carbon dioxide and this water is being produced? How many of these molecules of the reactants do I actually need in the reaction, right? So our alkanes burn with non-smoky flame. So my alkanes, when they burn, it is a clean blue, non-smoky flame. All right. Now, you will see this when you light your stove. So, you're cooking something, you light it, it's a nice, pretty blue flame. Just to show you the difference when we talk about a clean blue flame versus a smoky flame, ladies. All right, so look at these examples here, right? And so over here where you see that red orange flame, this is not an alkane. So this is what we call a smoky kind of flame. This kind of flame will produce a lot of smoke. If you think about a candle burning, your light is gone, you light a candle. Think about that. That flame is normally orange and a lot of smoke comes off in the atmosphere. Your alkanes, however, this is what they burn like. This is what we call a clean blue flame. All right. So this is what we always say it burns with a clean blue flame. This is the look that we want. Versus this. This orange is a smoky flame. So here they gave us methane. All right. So methane is going to burn with a nice clean blue flame to produce carbon dioxide and water. Again, it's just a matter of balancing off these reaction, ladies. So we want to do another example. So I am just going to choose any random number. So suppose we had a reaction with a carbon. So I want you to actually give me the formula for this one. So we want to do a combustion reaction, but my alkane has, I'm just picking a number here, ladies. Let's say it has 6 carbon atoms. How would I write my formula for an alkane with 6 carbon atoms? So we have C6H14. Can't be 12 because we're substituting. Wherever we see N, we're going to substitute 6. So C6H14 plus oxygen. I remember now this is going to produce carbon dioxide and water. Now, our challenge is, oh, by the way, help me put in the state symbols, ladies. What will be the state symbol for oxygen? Thank you. What's the state symbol for carbon dioxide? What's the state symbol for water? Gas. In this case, it's gonna be a gas. It's normally a liquid, but because we're just burning directly, it's gonna come off as a water vapor in this part. All right. Now my hydrocarbon has 6 carbon atoms. Is it going to be a gas, a liquid, or a solid? Liquid. All right, now ladies, we need to balance. All right. So the balancing may not be as simple as when we have like a double displacement reaction or something, but let us try. All right. Now, remember the rules for balancing. We have carbon, hydrogen, and oxygen. The rules suggest that you balance carbon first, hydrogen, leave oxygen for last. So let's play around a little. If I were to balance the carbon, what do I put? 6. Thank you. We're playing around a little. All right. Now, me putting 6 here, did it affect hydrogen? Affected oxygen. Balance of hydrogen now. I have 14 here and I have 2 over here. So now my carbon and my hydrogens have been balanced. We need to check for our oxygen. On my reactant side, I have 2. But on my product side, I have 6 times 2, which is 12, plus 7 times 2, 7 times 1, which is 7. So how much is this? So 12 plus 7 is 19, and we have 2 here. Can 2 go into 19 without leaving a remainder? All right, so this is the same thing as 19 over 2. All right, because remember that we would have divided the 19 by 2 to get the number here, but we're not going to write a fraction. So what we're going to do is to get rid of the fraction, we're going to multiply everything by 2. To get rid of the denominator, we're multiplying out everything by 2. So what would that look like now? It means that I'm going to have 2 in front of my C6H14 because there was no coefficient there. 19 over 2 times 2 over 1 is the same thing as 19. I remember that is what we were striving for. So this now becomes 19. We need to multiply my 6 by 2. This becomes 12. And then we need to multiply my 14, my 7 by 2 to get 14. So we're going to do a quick check, ladies. Is our equation balanced? No. This is something that you have to practice, ladies. Right? Is my equation balanced? No. Let's look. How many carbons on my reactant side? We'll come on to, when it comes on to combustion, ladies, you're going to find that some are doable, like it's not going to take that much effort like what we just did. However, a number of them are like this. And so it's a process of balancing that you must practice and understand. You're going to get a fraction when it comes on to oxygen. You can't write a fraction, and so you multiply the entire equation by the denominator to get rid of the fraction, right? Don't worry about the large numbers. It will all balance out at the end. All right. Last reaction now for my alkanes. Alkanes undergo what is known as a substitution reaction. All right. So there are two types of reactions that you're going to learn about, ladies. You're going to learn about substitution reaction and you're going to learn about addition reaction. Right? And it sounds like what it says. To substitute something, we are swapping out one thing for a next. When we talk about addition reaction, we're adding substances. So remember we said that our alkanes are saturated. It don't have any more space for anything else, ladies. So the only type of reaction it can undergo is a substitution reaction. You can't add anything else to it. So addition is out of the question. All right. So let us look at how the substitution reaction is. Now, usually the substitution reaction occurs with halogens. So remember we practiced yesterday about having the branch, you're right, having the halogens as the branch group. Let's look on it. So our halogens are able to replace hydrogen atoms for an alkane in the presence of bright sunlight. It occurs in stages where one carbon atom is substituted at a time. All right. So it is important to know that no reaction occurs in the dark, but the reaction is explosive in sunlight. So guess what? This reaction we will not do at a school level, ladies. All right, because we don't have that much added protection to do it. So this we won't, we just learn about it here. So halogen is going to replace a hydrogen atom one step at a time. All right. Now, notice that they have given us the molecular formula. But again, we are learning molecular formula, condensed formula, structural formula, because we have to prepare. We don't know what they're going to throw at us. All right. So this reaction is methane reacting with bromine. All right, so we're going to be looking at substitution reactions. All right, substitution reactions of alkanes. So remember that the substitution reaction is taking place, right? So we have halogens replacing one hydrogen atom, right, at a time. So this is what is taking place. So my halogen is replacing my hydrogen atom one at a time. All right, so we are going to look on it with bromine. Now I'm going to take it the easier route for you. What I'm going to do, we're going to take it with using the structural formula first, then the condensed formula, then the molecular formula. All right, so the reaction is between methane and bromine. That's the reaction, methane and bromine. So let's start with our structural. All right. How do we draw methane? We have meth, so how many carbon atoms are present? Length 1. So we have one carbon atom, and this is going to be surrounded by 4 hydrogens. All right. Now, what this is reacting with is bromine gas. Do you remember how to write the formula for bromine? Bromine is what should I say now? There's something about bromine of how it exists naturally in the atmosphere, much like oxygen. Bromine gas is Br2. All right, ladies. So bromine is a diatomic molecule and it is Br2. So to write the structural formula for bromine, I actually write Br-Br because the bromine atoms have bonded covalently, just like the methane structure. So it is Br-Br, where the dash means that there are a pair of electrons being shared covalently. So what is it that is happening now? What will happen is that one bromine atom will replace one hydrogen atom. So that is what is taking place. Now, if that happens, ladies, what's my new compound that I'm forming here? So remember, it is a substitution. What is going to happen on top here? I'm going to have Br on top. And then what is left is my hydrogen and my other bromine atom. All right. Now remember when we are naming our structure, right? We need to add the prefix for bromine, which is bromo. So this here now is bromomethane. But the reaction is not finished. All right, so the reaction is not finished because we have other hydrogens to substitute. So this is stage 1. So now we're moving on to stage 2. So let's look at what is happening now. My bromomethane here is going to react again with bromine. The bromine is going to substitute another hydrogen atom. All right, so that's the substitution reaction. So what is being formed now is that we have 2 branches of bromine. So my compound now is dibromomethane. But again, not finished because there are 4 of them. So now we have our stage 3. So our stage 3 now this is our bromine substituted, reacting with our another bromine molecule there. Bromine again, substitution of my hydrogen. So substitute, substituted, substituted. And then I have my HBr. The name of this now will be tribromo. Because there are now 3 bromines substituted. Then the last stage, which is stage 4. Bromine again is going to substitute All right, and this is what is being formed now. So all my hydrogens have been substituted. So what is being formed now is tetrabromomethane. All right, so let me make it smaller for you to understand what is going on. Can I get no? Still not getting all 4 stages. All right, there we go. So these are our 4 stages. Let's see if we can do the same thing, however, not with our structural, but with our condensed formula. All right, because again, you may end up with all one out of the 3 and we don't know which one. So we are starting off with methane. Now remember that methane only has 1 carbon atom, ladies. So the condensed is pretty much the molecular formula. All right, so methane is CH4 plus Br, right? And we have Br2. It's pretty much the same thing. Let's see. These things are not going to move out of my way. All right, let me pull this over just. All right, good. They're right in my way. So what is going to happen now, ladies, right? My condense, look on it. I have 1 carbon, 3 hydrogens, and a bromine. So if 1 bromine, remember I have CH4, and if a single bromine, as a matter of fact, let me draw out bromine. If a single bromine atom is going to replace 1 of my hydrogen atoms, this is going to leave me with 3. So this is my condense CH3Br, and then I have HBr over here. All right, same name. So this is my stage 1. Stage 2, I now have my CH3Br reacting with bromine again. Again, 1 is going to substitute here, and so I am left with CH2, sorry. So now I'm left with CH2, Br2, and my HBr. My stage 3 is now CH2, Br2 plus BRBr. You got to substitute again. So now we are down to CHBr3 plus HBr. And we continue substituting. Right? So this is what it would look like. For the reaction, they may ask you what observable change. All right. So remember now you're doing chemistry and these are all experiments being described to you. They may ask you what is the observable change. So in this case, my observable change, if it is bromine. So remember bromine has a reddish brown color. All right. Eventually, this reddish brown color is going to go to colorless. So here they said it says that a visible sign of this reaction is a rapid decoloration of the halogen. Bromine changes from reddish brown to colorless. If they were using chlorine, If they were using chlorine, ladies, remember your chlorine is a pale green. It's a pale green gas, and so that will be your color change, pale green to colorless. All right, now what are some of these uses for alkanes? Why are they so important? One, they are used for fuel. And I've stressed that so many times about you and your cooking gas. They are used to manufacture other chemicals. So methane in particular is a good source of the hydrogen in the manufacturing of ammonia. Alkanes are also used as solvents. So you think of medicinal ointments and rubs, right? They use the solid alkanes. Paraffin, another word that goes with paraffin is wax. All right. So these are good solvents. They're also used as lubricants. So polishing waxes, all right, lubricating oils that are used in like the car. These things are made of alkanes. Write the complete combustion of the following hydrocarbons. So we have C3H8, C3H6, C1838, C1224, C920. So you're